design class in the computer architecture and engineering things 151 and 152. Yeah, so I was thinking about taking those maybe next year. Yeah. Yeah. Yeah, of course.
I guess the people in the control room are monitoring this, so in case anything goes wrong.
Yeah.
Okay.
I think it's
Great. That's very nice.
Wait, can I just, are you about to start very soon?
People come.
Yeah.
other people
I
out
was
there?
actually, I wanted to reach out to you because you're amazing in the semiconductor industry and all of that, and I feel like more women need to know about the industry in particular. I think I didn't know anything about the industry until I attended one of Semi's workshops a few years ago, and that's what inspired me to think about electrical engineering. And so I'm actually a part of a program called CS Kickstart, and I'm one of the lead directors, and I think yeah, and I think it's really important that we not only emphasize computer science, but also talk about related industries. So I was
Yeah, if they're interested,
yeah, I'm happy for
okay.
I'm interested. I think it's
Okay. Let's follow up. There. Okay, very well. Yeah, are you bringing started? Oh, there are people outside? Oh, there are people outside? That's nice. Oh. Nice. Yeah, no, I fully empathize with that. You've got to have energy to function. Awesome.
All right, let's get started. I'd like to welcome everyone to today's EECS Distinguished Seminar, and it's a wonderful pleasure to introduce our speaker today. We're delighted to welcome the Dean of the College of Engineering and the Roy W. Carlson Professor of Engineering, Professor Tsu-Jae King Liu, to present the seminar today. And I get the honor of saying a few words prior to her seminar about Tsu-Jae. So Tsu-Jae is a graduate of Stanford. She did her undergraduate, master's, and PhD at Stanford, graduating in the early 90s, and then spending a number of years at Xerox PARC, where she worked on some of the research related to work she'd done as a PhD student. She came to Berkeley in 1996, so she joined our faculty in EECS in 1996. and started to work in and build up the department's work in semiconductor devices and semiconductor manufacturing. Over the years of being a professor and working on her research, she's done a number of amazing things, but maybe one of the coolest things that has gone all the way from kind of her, with colleagues' initial design, and now is in most of the transistors designed today, is a design called the FinFET. So FET is a field effect transistor, and it's called a FinFET because it has a little fin. So previously, these transistors were planar, and Tsu-Jae and her colleagues showed that by adding a little fin outside of the plane of the original transistor, they were able to increase the surface area, but also get like better control of the electric state of that transistor. This is now the basis for modern nanoelectric semiconductor device fabrication. So that's one big example, and you know, I think Tsu-Jae's path through that, from like the design and the proof of concept in a university environment, but then also like going out and working on this design in industry. So she started a company called Progressant Technologies, which was acquired by Synopsys in 2004 and holds 94 patents in semiconductor devices and fabrication methods. On the academic side, she has authored or co-authored more than 500 papers related to her research in this work. So just to say a few words about kind of the, you know, in that research progression, she was also a leader throughout that. So at Berkeley, she has been the faculty director of the UC Berkeley Microfabrication Lab. She joined Synopsys. So Synopsys is the company that bought her company, and she was the senior director of engineering of Synopsys for a while. She was also the associate dean for research in the College of Engineering at Berkeley, faculty director of the Marvell Nanofabrication Laboratory. And then from 2012 to 2016, she was the chair of first the EE division and then the chair of the department, Electrical Engineering and Computer Sciences, and of course now she's the dean of the whole College of Engineering. Just to say that she has just been nominated, and she's the only nominee to take on the presidency of the National Academy of Engineering, and that is going to happen next year. So that's really a cool thing. To a couple more words, she's won a number of amazing awards. I'm just going to list a few. So for the technologies that she's developed, she's won the DARPA Significant Technical Achievement Award in 2000, the IEEE Kiyo Tomiyasu Award, the Intel Outstanding Researcher in Nanotechnology, the SRC Aristotle Award, and she's a member of the National Academy of Engineering. But that's not all. She's also won awards related to her teaching and mentoring and her ability to really bring teams of people together to work on these big problems. She's won the EE Award for Outstanding Teaching. She's won a UCB Faculty Mentor Award for mentoring her students and postdocs within her group. And then just this year, she won the IEEE Founders Medal. And that really points to the work that she's done throughout her career, but also as the leader of the American Semiconductor Academy, which is an organization that she was instrumental in developing. And the goal is to really pave the way for the next generation of innovators and engineers. So welcome, Tsu-Jae.
Thank you so much, Claire. Can you all hear me? All right. Good afternoon. It's wonderful to see you all here. Thank you for coming in person. I know there are probably some people watching online. You know, thank you so much for that gracious introduction. I really would not have been able to accomplish, you know, all that Claire described without the wonderful colleagues, you know, students and faculty collaborators here at Berkeley, for which I'm really grateful. So for today's talk, it's more of a high-level talk for non-experts in my field, really talking about how we've entered into the age of artificial intelligence and what to look forward to in the future. But let's start first looking at how we got to where we are today. So artificial intelligence really requires real-time computation of large amounts of data. And if you look over time, over the last 120 years, the ability for computing devices to process lots of data in large quantities, like calculations per second, has grown exponentially. So this is a logarithmic scale. I'm just showing the calculations per second per dollar for different technologies. So in the most recent few decades, we've relied on integrated circuits or chips to do the computation. So if you look at this chart, it's not surprising then that we saw the advent of generative AI, ChatGPT, a couple of years ago, because the capability of computing devices today exceeds that of the brain of some small mammals. So chips actually are part of the foundational technology. So solid-state devices, integrated circuit chips, of course, you have to design the computer architecture and have systems of computing and data storage devices, and they're all networked together. And of course, the algorithms and the software written have to be designed to run on the hardware for specific applications. So this backbone of AI largely is at the foundation are solid-state devices and chips. And so it's not surprising that exponential improvement in computational ability has largely been enabled, not solely, but largely been enabled by the rapid increase in the complexity of these chips. So the number of transistors on a chip has roughly doubled every couple of years over the last more than 50 years. So today's most advanced processor chip, some of them, here's one example, have over 100 billion chips on a single die, smaller than the palm of your hand. The Blackwell GPU actually comprises 2 die, each having about 104 billion transistors, and they're interconnected together and with a very high-speed interface, 10 terabytes per second of passing data back and forth between those two processors to form the GPU. All right, so the outline of my presentation today is really to make sure that everybody understands how the industry has been able to make exponential progress over the last 50 or almost 60 years. Take stock of where we are at today. What is the trend that we see, and what are the challenges and therefore the opportunities for university researchers to contribute to ensure the continued growth of the applications of AI. All right, so to understand Moore's law, you have to understand the basics of how those chips are fabricated. So they're fabricated in many hundreds or thousands at a time from a single wafer, a single crystalline piece of silicon, and it has a very atomically smooth surface. So a wafer today, the most advanced fabrication facilities is about 12 inches in diameter, about the size of a medium pizza. And so depending on the size of the chip, a wafer can have hundreds or thousands of chips. And the chips comprise many layers of material. They're built up one layer at a time. So you coat the surface of the wafer with one layer of material, then you coat it with a light-sensitive material called photoresist, and you expose that photoresist with monochromatic light, typically in the deep UV ultraviolet range, through a mask. And there's some optics, some optical column that reduces the size of the features onto the wafer. So usually you expose that photoresist one or more dyes at a time, and typically you expose the entire wafer within 1 minute. Okay, so then what happens is the photoresist is put into, the wafer is immersed in some developer solution, and that removes the photoresist in all the areas that saw light. Okay, in that manner, the pattern of the mask is transferred onto the photoresist on the wafer. And then the next step is to subject the wafer to an etch process. That etch process removes the layer that we deposited in the regions that are not protected by photoresist, because the photoresist resists the etch process. And in this manner, you transfer the pattern from the mask to the photoresist to the wafer, and then you strip the photoresist. So dozens of layers are built up one by one on the wafer, and then after that, after the wafer is processed through about 1,000 steps today, then the wafer is singulated into individual dies, and the dies are packaged to be inserted into your electronic system. So Moore's law is really a law of economics. If we can actually improve the resolution of that lithographic patterning process by 30%, just a little bit, each generation of technology, then we can actually make the transistors, the individual components that make the integrated circuits, the transistors smaller and pack them more tightly together. And that actually allows us for the same functionality. So you have some memory, some input-output circuitry to interface with the system, and you have some computing digital logic circuitry. So the same circuitry can be fabricated on smaller and smaller area, so you can fit more dies on a wafer. And so if the wafer fabrication cost is not changing too much, then the cost of manufacturing the same function of a chip goes down. And alternatively, you can keep the chip the same size, but increase the number of transistors. So you can actually also increase the functionality of a chip by advancing the technology this way. So this has allowed chip designers to design and produce more functional chips for lower cost per function, and companies derive revenue, and then they can invest a portion of that revenue back into advancing the process technology to make it even more high resolution and precise. And so this virtuous cycle has gone on for over 50 years. Now, part of that virtuous cycle is that you make profit. So companies sell more and more chips. A lot of the chips are used now for Internet of Things. So at home, on the roads of cars, have over 1,000 chips today, the new cars. At home, you have the smart thermostat, you have security cameras, right? You have smart appliances. So these these devices, which are not in the cloud, but physically, like on people or around us, there are billions of them together today, and they're all connected to the internet or wirelessly communicating with each other. And this trend, driven by Moore's law, predicts that we're going to have dozens of smart interconnected devices within the next decade per person. Right? So the number of chips and smart devices is growing faster than the population. So it's not surprising if you look at the amount of data generated in the world every year, that the amount of data generated by devices rather than people, like creating YouTube videos, has surpassed the amount of information generated by humans. And it's projected to grow to over 100 zettabytes. Yes, and notice industrial IoT devices, like in factories, and then in autos, lots of sensors, and also in the home. And humans, we're not going to grow that quickly in terms of population. So today we live in a data-centric world. And also it's because we're able to collect so much data and process it that AI has come onto the scene, right? You need a lot of data to train the AI models. Now, at the same time, the industry has done more than just shrinking transistors. They've actually incorporated different types of devices into these electronic systems. So the same kinds of processes, depositing a film, patterning it using photolithography and etch, can be used to make different types of devices. So not only electronic devices for computing and storage of data, but communication devices, microelectromechanical systems, so sensors, inertial sensors, like to sense rotation and movement, photonic devices that are sensitive to light and so on. All kinds of sensors can be fabricated using the same thin film fabrication process techniques used to make transistors. So this is how the industry has been able, the electronics industry has been able to develop more functional devices that we have come to depend on today. Now, decades ago, we were thinking, generally technologists were thinking, well, if we want to incorporate more functionality in a system, then we need to figure out a way to stack all these different types of devices on top of transistors. Okay, so in addition to the microprocessor and memory devices, analog to digital converters and RF transceivers and receivers, well, if we want to put sensors in a system, we have to make them compatible with the digital electronics. So there was a lot of research finding ways to fabricate these different types of functionality and somehow integrate them, stack them together over the circuitry. At Berkeley, we had a lot of researchers looking at ways to just, after you fabricate the circuits, how do you fabricate additional things on top? Here's an example of a microelectromechanical switch that I'll talk about later. So at Berkeley, just this is too long of a timeline. These are just some examples, some milestone achievements in the microlab here at Berkeley, which has now evolved into the nanolab in this building. So Professors Howe and Moeller, they showed integrated organic vapor sensor with some circuitry. Professor Moeller looked at even more a complex pressure gauge, integrated with CMOS circuitry. And then other types of, here's a comb drive resonator invented by people like Professor Clark Nguyen in our department. At Berkeley, one of the first things I worked on when I joined the faculty here was collaborating with Professor Roger Howe. How do we develop a very low process temperature technology to enable these MEMS, microelectromechanical devices, to be fabricated directly on circuitry, because the circuitry cannot withstand more than about 500 degrees Celsius. So these, and then Professor Boker, a former department chair as well, his group was the first to really demonstrate integration of carbon nanotubes, which could be good for computing or for sensors on top of conventional CMOS circuitry. Okay, so that's kind of a retrospective look. Now let's look at where we are today. Because of Moore's law steadily advancing the resolution of the manufacturing, the lithographic patterning process, today in a state-of-the-art chip, the minimum feature size, let's say the width of these silicon fins, so that as Professor Tomlin mentioned, the silicon now, we pattern it into tall, narrow fins and wrap the control electrode around it to provide for better control of the electric performance. The width of those silicon fins is about 5 nanometers. So that's 10,000 times smaller than the width of the diameter of your hair, okay? And insulating the gate control electrode from the silicon fin is a layer that's roughly 1 nanometer thick and is deposited by atomic layer deposition. So we are seeing atomic level precision of thin film thicknesses on wafers that are macro scale, right? The size of a medium pizza. So that's a pretty high precision process. So semiconductor manufacturing today is probably the most complex, most sophisticated manufacturing process on the planet. Now, if you take all the layers of metal interconnects to connect those 100 billion transistors together, there are about more than a dozen layers of metal wiring needed to interconnect all those transistors to perform the function that the designer intended. If you take all of those segments and laid them end to end, they would span dozens of miles. Okay, so that's all fitting on a chip smaller than the size of your palm. Now, the lithographic patterning process, if in the fab, if a dust particle falls on the surface, well, it can block the exposure of light, right, to the photoresist, and you can end up with a faulty pattern transfer from the mask to the wafer. So what the companies do is they inspect the wafers at each step, and if they find a defect like this, they can rework the wafer, like they can just strip the resist and try again. Okay, so the wafer inspection process is equivalent to spotting a single ant from outer space, identifying its species, like determining if it's going to be damaging, detrimental, in less than 1 second. Okay, just to put things in perspective. So then it shouldn't be too surprising that today's most advanced chips, I don't know, this thing's not working. I'm trying to advance my slide, but it's not working. Okay, my computer's hung up. Pardon me? Let me see. Let me try again. Okay, let's try again. All right, so it's not surprising, I hope, that these fabs nowadays cost over $10 billion, closer to $20 billion after you've outfitted them with equipment, $10 or $20 billion to build. And so to get the most to recover that large investment, companies really have to design them to process wafers at tremendous scales. So a typical state-of-the-art fabrication facility today processes 12-inch wafers in diameter. They go through over 1,000 process steps, and they process over 100,000 wafers per month. Okay? Now, very few companies can afford, okay, the 100,000 wafers per month. Imagine how many chips that produces. Very few companies actually sell that many products to fill a fab. And if you don't fill the fab, then you're not going to recover your investment, and so you don't have a viable business model. So this is why only a few companies today can afford to have their own fab. So these are companies like Intel, Micron, Samsung, SK Hynix. A lot of these are memory chip companies, TI. So what has emerged over the last more than 2 decades is the fabless model, where companies like AMD, Apple, NVIDIA, Qualcomm, they actually outsource the fabrication of their chips. And together, the foundries, like Global Foundries and TSMC, they can fill their fabs if they are fabricating products for all these companies. And the only thing they need to do, those companies, is to provide the mask set. Okay, so the foundry interacts with the fabless companies by providing them with a process design kit. It lays out rules like how all the patterns for each mask layer should be like aligned or not too closely spaced. So as long as these fabless companies design each layer of the integrated circuit to follow the design rules in the process design kit, the foundries guarantee they can manufacture the product. So the nice thing is the same sequence of about 1,000 steps can be used to fabricate all kinds of different products. Now, it's not trivial to even design a 100 billion element system. Imagine if you had to design something like that has 100 billion components, that would take a while. So to enable companies to design chips in a timely manner, the electronic design automation industry has emerged. So you have software that helps to automate a lot of the design that ends up with the mask set that follows the process design kit. Also, there are companies like ARM Holdings that already have pre-designed blocks, so that companies, if you need a standard input-output block or some other computational block, you can just take the design license, pay them a license fee, and plug it in and just fit it into your chip design. And there are other companies like PDF Solutions that provide engineering services to help these fabless companies make sure that the chips that are fabricated by the foundries actually function as intended. Now, at the same time, there are a lot of materials, chemicals, and gases needed to manufacture chips. They're supplied by various companies, wafer fabrication equipment suppliers, the companies that make the lithography tools. You might have heard there's one that makes the leading edge lithographic exposure tool that's in the Netherlands. There are wafer fabrication equipment suppliers in Japan as well as in the US. The chips, after they're singulated from the wafer, are assembled and tested usually overseas, like in Asia. So this whole ecosystem to manufacture chips is a global ecosystem. And this has resulted in some supply chain challenges for our country, which led to the Chips and Science Act to really try to encourage some companies to manufacture chips on American soil so that American manufacturers can have a guaranteed supply. Okay, so that's Moore's Law. What's changed in just the recent few years is that in order, we saw from the Blackwell chip, you actually don't have more chips on more transistors on a chip. You're actually starting to make multiple chips in a package. Okay, so this is enabled by advancements in chip packaging technology. So this is a chart from Intel showing the number of transistors per package, and they expect that Moore's Law will continue. It will evolve to be increasing number of transistors per package rather than increasing number of transistors per chip. Okay, and this is enabled. So this is an evolution of Moore's Law. In the past, we thought, well, if we want to have a system, integrated system, work well together, we don't want to move electrons in long distances between chips because that takes time and energy. But now with advanced packaging, you can actually make the interconnects between chips or chiplets very short. And so it becomes actually cost-effective and energy efficient and time efficient to assemble systems from smaller pieces of silicon and package them together rather than all stacked together on top of each other in a system on chip. Okay, so these are some cross-sectional views showing for Intel, they have, like, let's say 2 chiplets, and then they embed a piece of silicon with lots of high density of interconnects to connect these 2 chiplets together. So this is a chart from Applied Materials, one of the equipment manufacturing companies, looking at the input-output density of a chip. Like how, in the past, maybe you'd have a connection between your chip and the printed circuit board, PCB, and it'd be, let's say, less than 100 input-output signal lines per millimeter squared, and it'd cost this much energy, picojoules, per bit of information to transfer between the dies. With advancements in packaging technology, the amount of energy needed to transmit signals between chips is going down exponentially, and the density of interconnects between chips is going up. So this provides for essentially better energy efficiency, so that so it makes sense to package chips together rather than try to make dies bigger and bigger. Part of the reason is, I'll explain, well, the number of steps I mentioned is over 1,000 steps. Today, it costs, at the leading edge technology, like 2 nanometer generation technology, the cost of a 12-inch wafer is over $20,000 to the customer. And you might have read in the news that people are thinking that it might cost, TSMC might charge over $30,000 a wafer in the future, because they can, they're the leaders, right? There's no other foundry at the leading edge. So that's not Moore's law, right? A decade ago, a wafer, the leading edge wafer would cost a few small, like thousands of dollars, $3,000. But now the same size wafer with the more advanced technologies, 10 times more. So remember, Moore's law is all about just improving resolution, not increasing the number of steps. You don't double the number of steps to double the number of transistors, right? There's no cost benefit. Same number of steps, just a little bit more precise, then you get some benefit. So Moore's law, yes, is evolving because the cost of fabrication is really going up, which is not the original Moore's law. So on this slide, really in the future, with advancements in chip integration, the package actually helps to provide value in terms of system performance and energy efficiency. And interestingly, by allowing companies to fabricate integrated systems with chiplets, that allows different chiplets to be fabricated using different processes. Right? They don't all have to be fabricated using the latest 2 nanometer technology. And it's cheaper to fabricate dies with older generation of technology if you don't need that level of density or performance. So this is another reason why it's good from a cost perspective to have chiplets, because you can have older process generations or nodes used to fabricate a lot of the chiplets, and only the most advanced part of your system needs to have be fabricated on the leading edge technology, and that can be relatively small, and making it small also makes it lower cost for that generation of technology. Okay, so looking forward, how do we expect this technology, the foundation for AI to continue to advance so we can see AI continue to proliferate? Well, the Semiconductor Research Corporation, or SRC, has published a decadal plan to guide research investments to advance information and communication technologies. So they've listed various grand challenges to enhance the ability of future microelectronic devices to sense the world around us, to store more and more data, communicate more quickly and more energy efficiently. Turns out, like for mobile devices, sometimes more energy is used to communicate data than to process data in your mobile device. How to ensure security? If you're passing data, communicating it all over the place, how do you ensure security built into the system? And in the news, more and more is energy efficiency. So you might have seen news this week, I think it was this week, that Google signed a deal with Kairos Power. It's a startup out of our nuclear engineering department, by the way, for medium-scale nuclear reactors. So Google plans to be using nuclear reactors to power its data centers. So let's just think about this. A GPU, the Blackwell GPU, it full blast, it burns more than 1,000 watts, like 1,200 watts. So let's say that's 1 kilowatt. And in a data center, or how many GPUs do you want in a state-of-the-art data center? 10,000 or so? Okay, so that's like over 10 megawatts. That's enough to power a small city, right? So, so energy consumption of computing is actually a challenge. So let me talk about that for the rest of my presentation, because the title of my talk is about disruptive innovation. So let me first explain why digital computing has an energy efficiency limit. So this is a cartoon diagram of a transistor, the kind used for digital computing. You have a gate electrode that controls current flowing between the source and drain electrodes of a transistor. And the source and drain electrodes are just heavily doped, or they're very conductive regions of the semiconductor. And the gate electrodes electrically insulated from the silicon by that thin insulator I mentioned earlier. So transistor in digital circuits operates very simply as a switch to turn on or off. And when it's on, it allows current electrons to flow between the source and drain to equilibrate the electric potential between these two electrodes. So if you look at the current versus the gate voltage, the voltage applied to the gate, there's some minimum threshold voltage that you need to apply to the gate in order to turn on the transistor. So on a log scale, the current increases kind of linearly above the threshold voltage. Below the threshold voltage, the current comes down exponentially, but the key here is that even with no voltage difference between the gate and the source, there's some off-state leakage current that flows. In other words, the transistor is an imperfect switch. Now, in the on-state, when you apply the full voltage, the supply voltage, VDD, onto the gate and the drain, you have some on-state current. So the current level determines how quickly your circuit operates. The more current your transistor conducts, the faster it can move charge around, and the faster the circuit operates. But if you want to save energy, then you want to lower the supply voltage, and that can reduce, so you can reduce the energy needed to charge and discharge different parts of the circuit if you lower the voltage to which you're charging and discharging. But that means that your circuit's operating more slowly because lower current in your transistors. Now, if your circuit operates more slowly, then most of the circuit is not switching, it's just static, and transistors are leaking current. So it just turns out that to perform any particular digital operation, the longer it takes to perform that operation, the more energy that's wasted due to just transistor leakage current. So then you can see, and you can avoid this if you lower the threshold voltage of the transistor. You design the transistor to have lower threshold voltage so the speed of the circuit is not compromised, but then the off-state leakage current goes up. So no matter what you do, there's a trade-off in the static power dissipation, energy dissipated versus dynamic. And so for any CMOS, the digital computing technology, there's some fundamental minimum energy needed to perform the operation. And that turns out that that's around the threshold voltage of the transistor. And let's say today's anywhere between 0.2 and 0.3 volts. Okay, Professor Tomlin mentioned that at Berkeley we invented or developed the FinFET. So now we allow the gate to wrap around. If the width of the fin is smaller than the gate length, then we can get really good control. So we can get steeper turn-on characteristics. This allows us to operate at lower voltage and still have high I on, high I off. And this is why, starting in the early 2000s, it caught the attention of the industry. Intel was the first to put it into high volume production. Now the width of the transistor now is just the height of the fin. It's a big manufacturing challenge to make tall and narrow fins. So if you want to have the transistor conduct more current, you have multiple fins in parallel like this. So over time, we've evolved from planar transistors, gate, source, drain like this, and a planar silicon surface, to FinFET. And you can just see the fins are getting taller and narrower as you advance the technology to allow for more current in a given area. And now the industry has gone to so-called gate-all-around transistors, where the gate not only wraps around 3 sides, but around all 4 sides. And then we stack multiple silicon channels, semiconductor channels on top of each other. So we call these stacked nanosheets, or Intel calls them nano ribbon devices. Okay, so you can imagine the amount of extra steps needed to fabricate this kind of transistor compared to a planar MOSFET. So this is only going to make the fabrication cost per transistor higher, right? So this is not necessarily the solution for all kinds of devices, especially Internet of Things, edge devices. So this is why I think there's an opportunity here for disruptive innovation. Yes, the definition of disruptive innovation is something that is an innovation that is starting out, is somewhat inferior to the incumbent products, but it has some acceptable performance characteristics. So this is a chart taken from a paper in the Journal of Management Studies. So this is a plot of product performance versus time. So you can have low performance products, mainstream products, and high performance products. Over time, I guess all of them, customers are willing to pay more for them over time. And so typical, let's say, incumbent company in an industry, they are always seeking to go steeper, improve their product performance over time more steeply than this, this natural curve, because they want to be able to sell higher performance products for a higher profit margin. Okay, so a disruptive innovation company might enter this starting with the low performance end of the market, and again go on a steeper curve And so this is just the definition of disruptive innovation. They can be smaller, cheaper, more accessible, more convenient. Okay, so I'm going to give you one example. At Berkeley for the last 15 years, my research group has been looking at mechanical switches, which, if you remember, one of my first slides was showing the ushering in the age of AI. If you noticed, in the early 1900s, mechanical switches were used for computing. Okay, we're going to go back and look at mechanical switches, because now we can make them to be nanoscale. Okay, and the advantage of mechanical switch is that in the off state, you have a gap between the two conductive electrodes, source and drain. So you have zero leakage. Remember, energy efficiency limit is due to leakage of a transistor. Now you can apply a voltage to the gate electrode relative to the source to induce an electric field. The strength of that electric field depends on the voltage you apply between the gate and the source, but also on the gap size. The smaller the gap size, geometrically higher the electric the force induced by the electric field. Now in the on state, there's contact adhesion, so that when you remove the voltage to allow the spring restoring force of this electrode to pull the switch off, there's some hysteresis. Okay, so over the years we've been finding ways to reduce that hysteresis voltage, and so in principle you can apply, this is the same curve as the transistor IV characteristic I showed earlier, current versus the applied gate voltage, but now notice once contact is made, current suddenly increases, it's limited by the contact resistance, and when you lower the voltage of the gate, the current suddenly drops down. So in principle, this switch can operate with a gate voltage swing of millivolts rather than volts compared to transistor. So zero leakage and 10 times lower operating voltage than transistors. Now the switch I showed on the previous slide is pretty simple. The voltage difference between the gate and source determines the state of the switch. But in an integrated circuit, like when you do digital logic computation or operations, you don't really want the source voltage, the gate voltage to depend on the source, the turn-on voltage to depend on the source voltage. So in our group, we looked at a 4-terminal design where you have an extra body electrode, and it's the voltage difference between the gate and the body that determines if this relay is on. And we can incorporate more than one set of source and drain electrodes, so you can actually have 2 electronic switches built into one movable structure. And the nice thing here is that the source voltage can be high or low, and so this switch can pass, when it's on, it can pass a high voltage, VDD, or it can pass a low voltage. And if you know about transistors, the N channel, the negative channel, the charge channel transistor I showed in the previous slide, you have to apply minimum voltage above 0 to turn on the switch. So a transistor cannot fully pass a high voltage for an N channel device. For the opposite type of device, a P channel device, which conducts with positive carriers, it cannot pass a low voltage through. So basically, a relay is a more perfect switch in many ways compared to a transistor. Now this is a scanning electron micrograph of a microelectromechanical switch. This is the movable plate, and underneath it is the body electrode. So we apply voltage to the gate. It's suspended by these 4 springs in the 4 corners, and actually integrated underneath there are the source and drain electrodes. So this has 2 sets of source and drain electrodes. The structure is a polycrystalline silicon germanium, which is what we developed for integrating MEMS with CMOS many years ago, but has good structural properties. And the electrodes here that we use are tungsten. So we fabricated these devices using standard microfabrication techniques. Here's a cross-sectional view. The source electrode is routed underneath that movable gate structure, electrically isolated from it by a thin gate oxide. So keep track of the contact region here. Here's the source electrode fabricated over the drain. What we did was we selectively removed a layer in here as a final process step. So there was an oxide, silicon dioxide layer here that was selectively removed to allow to form the air gaps. So when we apply a voltage between to this gate relative to the body, it brings the relay into contact. But we can lower the gate voltage needed to operate this switch by pre-biasing the body. So we bring that structure down close to contact so that the amount of voltage needed to turn on and off the device is very small. Furthermore, if you apply a negative voltage to the body, then that lowers the positive voltage needed to be applied to the gate to turn on the device. But if you apply a positive voltage to the body, then you can actually turn on and off this device by not increasing the gate voltage, but decreasing it. So you can get complementary relay operation, like an N-channel and P-channel MOSFET with a single device. You don't have to have any extra process steps to make 2 flavors of a relay. You just need to change the body bias voltage. Okay, so very quickly, my group has demonstrated that with this body biasing technique, we've demonstrated like a simple inverter, right? The input is this, the output is just the opposite inverse, right? If it's high input, then it's low output. And we operated at 50 millivolts. This is a little more complex function, but it still only requires 2 relays, multiplexing. So just trust me, it works. 50 millivolts. But if we lower the operating temperature, we can actually get the operating voltage to be 25 millivolts. So like I said, it's 10 times lower operating voltage than the silicon-based transistors, okay, and has 0 leakage. All right, so this is possible. Now, furthermore, that body electrode, you can partition it into multiple electrodes that are separately biased. Actually, no, you can call that the gate. So you can actually have in the same structure multiple input signals coming in to determine if this relay should be actuated down or not. So depending on the body bias, okay, notice we're changing the body bias, we can turn on the relay if all 3 input voltages are high, or if only one of them is high, or if a majority of them is high. So you can cause the switch, you can design a switch to perform much more functions, many more functions than a transistor. Okay, so these are just waveforms that show that just by changing the body bias, we can actually, for the same set of input voltages, we can get different switching characteristics just by changing the body bias. So and majority functionality. Okay, so that MEM relay is kind of large, if you noticed. Well, we can shrink the size. So that was actuated in and out of plane of the wafer. We can switch it so we can fabricate it so that it can move laterally in plane. This actually makes it possible to make a relay in this just 1 layer of material, so that can make it a much simpler fabrication process. Or we can vertically orient the beam to tilt it back and forth for the smallest footprint. And so my group has demonstrated this is possible. Today, the most modern chips, they have many layers of metal interconnects, and the industry knows how to make air gaps between them. So all you need to make a mechanical switch is metal and air gaps. And so this is an example of an even more functional mechanical switch where the beam is vertically oriented for high density, and then you can have conductive electrodes on the top layer of metal, and you can implement that actuation electrode, the gate electrodes on left and right side, and you can actuate the switch to the right or the left. So this is like a memory cell. And since this is on top of semiconductor, you can easily incorporate a diode to allow current to flow only one way through that switch when it is on. And so my students have taken a standard foundry PDK, laid out metal layers, and in the nanofabrication lab here, do a bunch of so the upper layers act as the mask, and so they protect the actuation electrodes and the conducting electrodes, and they expose the movable beam. This is a top view scanning electron microscope as fabricated after the beam has been actuated to touch one of the conductive lines, and here's a cross section. Okay, so we leverage IC technology advancement, so the more tighter pitch you make these metal features, the smaller the gap, and so that means you can lower the operating voltage. So we project that if we go down to beyond 7 nanometer technology, the operating voltages of these nano-electromechanical switches can be compatible with traditional, just standard transistors. So I'm just going to show you quickly. And this is a schematic this is a cross-sectional scanning electron micrograph showing the movable beam implemented with multiple layers of metal. Here are the FinFETs down here. Integrated circuits fabricated using CMOS and NEMS. This is a simple, this is a simple circuit that performs you can call it either a data searching operation or decoding operation. So this is a common operation used to route packets in the internet. It could be used for pattern recognition, and it's relatively compact compared to full only transistor implementation. Here's a lookup table. So for edge computing, rather than calculating the answer based on some inputs, you could look up the answer. So we demonstrated a lookup table that trust me, it works. And then the nice thing here is it's reconfigurable. So you can change the answers to adapt to the environmental inputs. And a lookup table performance comparison in terms of chip area, readout delay, and readout energy. CMOS plus NEMS together outperforms by orders of magnitude pure CMOS. And if you have only transistors, you need to load the answers from a non-volatile memory, put it onto static memory, input the address, and read out the answer. Here you just have one circuit with reconfigurable switches on top of CMOS. So interestingly, these switches they actually compare very well compared to other non-volatile memory devices. So magnetic RAM, ferroelectric memory. So if you care about energy efficiency, we're talking about orders of magnitude improvement in energy efficiency for storing information in a non-volatile manner. So my last slide here in terms of new technology, just relatively recently, it was published in a journal last year. In the future, we know that today, if we want to process lots of data, it takes a lot of time and energy to move data from memory to the arithmetic unit. So why don't we come up with new architectures to perform a computation directly on data stored in memory? So this is a class of architectures called in-memory compute. And this is an interesting paper. In one clock cycle, they could perform 2,000 multiply accumulate operations, 32.2 teraops per watt, or 4 teraops per square millimeter. The interesting thing is they implement this with a cross-point array of capacitive switches. And the back-end of line NEMS switch that I showed earlier actually could be made into, rather than a resistive switch, they could be made into a capacitive switch. Finally, for relays, going into space, near Earth orbit, how are you going to manufacture parts up there? I mean, we have to manufacture parts rather than bring all the parts we ever possibly could need up into space, right? So how do you manufacture chips in space? You're going to put a $20 billion fab out there? I doubt it. So interestingly, relays, we've already shown years ago that you can just inkjet print them. Okay, so this is an example. It just depends on the resolution of the inkjet printer. But we've demonstrated functional relays inkjet printed with silver nanoparticles. Also out in space, you have to worry about irradiation. So one of those 6 terminal relays I showed earlier, we tested dozens of them, subjecting them to gigarads, tens of gigarads of alpha particle radiation. And the pull-in voltage, the switching voltage, changed by maybe 10%, but if we took them out from after radiation, the pull-in voltage recovered over a period of hours. So these are all advantages of mechanical switches. So this is one example of something that could be very disruptive in the future, overcoming some of the challenges for proliferating AI. So to summarize, IC technology advancements have enabled the proliferation of AI. Moore's law is evolving to allow chiplets to be tightly integrated, and this actually presents new opportunities for innovation of new technologies that can be integrated together with state-of-the-art digital computing devices. So I do think that if we want to improve energy efficiency of AI by orders of magnitude, you do need some disruptive innovations. But these innovations, we're going to need collaboration across all those technology layer stacks. So it's one thing to come up with solid-state devices, but the circuit designers need to learn how to use them, be able to model them. They have to be reliable. And the computer architects need to figure out how best to use them. And then, of course, the people who develop the software stack also have to figure out how to co-optimize their algorithms and software for specific technologies. But I think by working together, we can address those challenges. And I think in the future, we'll see continued enhanced functionality of integrated systems. They'll be more sensitive. They'll be responsive to the environment. They'll be adaptive. Transparent means that invisible, you can't see them. They certainly will be ubiquitous, and they're sort of ubiquitous already. So in the future, we'll have these intelligent systems that actually will help usher in the age of ambient intelligence, where you have intelligent systems that help to run our cities and ensure good customized treatment in hospitals, operate our transportation networks, and so on and so forth. So I think this is a vision that's still not yet realized because of those challenges I mentioned earlier, but with disruptive innovations, I think we can get there. So I think that's it. I'd just like to acknowledge all the students, the collaborators, and the facilities and the funding that made this work possible. And lastly, thank you all for your kind attention.
Thank you, Tsu-Jae. We have some time for questions if folks want to ask a question. Catherine and I both have mics. We'll start with Carlo.
Thank you for a fascinating talk. So the last 20 years have been mind-boggling on the advantages on the chip level and so on. Now, the projection that we heard today is that most of that enormous computing power will go into AI. We can expect next 20 years going to be another factor of 100 or 1,000 times more computation. So my question is, what are other applications that can really use this much of compute power? Is it simulations of physical objects or devices? Is it the n-body problem in 3D? Or where do you think we can use all that compute power?
Yeah, that's a great question. I think a diversity of people will come up with a diversity of ideas, but certainly that one example you mentioned, digital twins, that takes a lot of compute power. So maybe in the future, the metaverse, when we actually simulate things in cyberspace before we actually design and actually build them, that's a emerging area for research in engineering in general. But that's just one of many examples where they can use all the computational power that can be produced in a cost-effective manner and energy-efficient manner. So I think that's the challenge. Please.
Hello. Thank you for a great talk. It was a really good high-level view of both your work and also the industry at large for the last couple decades. And one thing you really focused on was just how difficult it is to manufacture semiconductors, all these chips. And upgrading these factories is also very difficult, and I'm sure it's like a 10-year plan for a lot of these companies. How do you think the partnerships between research and industry are going to evolve to try to help them figure out what to plan into their upgrades for their factories over 10, 20, 50 years to increase consumer access to a lot of these advanced research areas?
Yeah, that's a great question. Even just the next 5, 10 years, what industry, there's a trend now, at least in this country, to bridge that so-called gap between research and manufacturing. So, for example, there's the Chips and Science Act. They do fund programs to bridge that gap. At Berkeley, we're co-leading a hub for AI, to advance AI hardware innovations more quickly into foundries. So I think a closer collaboration between industry and university researchers is definitely the trend, and that will help to ensure the companies have a better view of which directions they should go as they further advance the technology in the future.
Hi. Thank you so much for the talk. It was really a lot of, I was especially interested about the electromechanical parts which you were talking about for transistors. They were very novel ideas for replacement for these electronic switches. So one of the questions which I had on this was, why is there any reason why electromechanical switches is not mainstream right now? Like you mentioned hysteresis, but any other reason other than that? Because they seem to have all of they have so many more advantages as compared to electronic transistors.
Yeah.
So is there any reason why they're not mainstream?
Yeah, that's a great question. So as I mentioned, electromechanical switches were used literally over 100 years ago. Back then, when they were large, and so they were not as reliable. They took more energy than vacuum tubes and transistors, and they were not reliable. But it turns out, if you scale the size of a mechanical switch down to be comparable to that of a transistor, it actually becomes more reliable for various reasons, and it's less expensive. So all those challenges actually are mitigated if you go to nano fabrication. And at the same time, for a transistor, because that subthreshold swing, actually there's some limits. I know Professor Salahuddin gave a talk to explain how you can improve the subthreshold swing, that's turn-on slope. Because transistors, you need some minimum tenths of volts to turn on and off. even if you shrink them, you can't shrink that voltage, so the peak electric fields are going up because you apply the same voltage over a shorter distance. And so that causes reliability challenges for transistors. So now in this nanoscale regime, reliability is actually has been a challenge for transistors. There's a trade-off between speed and reliability. But mechanical switches don't have that subthreshold swing limit. No, as long as it's off, it's zero leakage. Yeah.
Thank you so much. I just had one more question, I'm sorry. The other question was, I was reading about compliant machines. Essentially, like, it's right now, I think, in the micro scales where you have these machines that have special materials that bend, and rather than they essentially comply with the external stress. So you have a lot of these, and they're very scalable because you can make a mold of it and just chop it up, and you can use them as lots of different macro scale applications like vices and stuff, like compliant machines. Do they play a role in like mechanical switches? Because technically when you apply voltage and the gate closes, you can use compliant
the scale of these things is so small that even if you have like something that bends on a nanometer scale, they're not really strained very much. Yeah, so that's not an issue. But that makes them, but that's a good point. These mechanical switches, they can be inkjet printed. They can be printed on anything. They don't have to be printed on a rigid silicon wafer that costs a few $100s, right? You can print them on literally paper or plastic. And so it can be much more compliant and conformal, like to the human body or other things that you want to apply some electronics to, right? So that's another example of an advantage of mechanical switches. So that's why I'm saying disruptive innovation. Incumbents, like companies like Intel, they're not going to look at this because, you know, that chart I showed you. But if you want to enter with some disruptive innovation, you got to aim for some niche applications where you definitely have some advantage that the incumbent cannot address.
One more question.
Yeah, thank you for this eye-opening talk. And I'm wondering for two things. One is, as you mentioned, the manufacturing for semiconductor have a lot of upstream and downstream dependency. So if you want to change something, a new paradigm in the middle, you need to involve change in the upstream and downstreams. And how are you going to convince the industry or change the entire industry to follow with your new paradigm? And the second part of the question is, I have been working with like memristors, and I know people are talking about carbon nanotube for in-memory computing or new form of computing. And how is your way of computing going to compare with other new paradigms like memristors computing?
It's a great question. The answer is yet to be determined because it really depends on the specific application. Right, so mechanical switches, they're great at ensuring two discrete states. But if you need something like an analog device, then the mechanical switch is not good for that. Maybe a memristor would be good. But it really is dependent. So I think people recognize that now we have to, what do you call it, the domain specific, but even like application specific hardware. That's why I'm saying we need collaboration across this backbone, this stack, because the answer to your question is not known until we optimize the algorithms with the architecture, with the circuits and the device, right? And for each different application, it could be a different solid-state device that turns out to be the best, the most optimal. So that's why we need collaboration across that stack. So when you say upstream and downstream industry, you mean like high volume manufacturing versus R&D?
No, like, so for people who are, so how do you want the industry to collaborate?
Yeah, so I think what we need to do is to collaborate. Let's say solid-state device innovators need to collaborate with integrated circuit designers and computer architects. But the key is, okay, just like between solid-state and devices and integrated circuits, we have process design kit. We need like accurate models to predict how the new devices behave, so that people downstream, is that downstream? can actually experiment, right? Try different applications, functions, and so on to figure out. So the simulation, the electronic design industry, I think they're also evolving so that they can simulate mechanical devices as well as other types of sensors, sensor devices now, as we want to enhance the functionality or the energy efficiency of these integrated systems. So I think it's really key, automation, accurate modeling, automation and collaboration. I think that's what's needed. But I think the opportunities are really, there's no boundaries. So a place like Berkeley, where you have experts across all of that all those stacks, this is where I think we can, working together, we can make a huge impact. Yeah, orders of magnitude improvement.
All right, with that, I'd like to conclude the seminar and thank once again our Dean, Tsu-Jae King Liu, for a wonderful seminar and all of the gracious question responses.
Right, go Bears.
Thank you very much.
Thank you, Claire.